An Analysis of Invasive Grass Establishment in the GOGA by Natalie Bartel and Jonathan Lowe. The Golden Gate National Resource Area, or GOGA, is an expansive Bay Area park system. Spanning from Marin to San Mateo counties, GOGA is home to 19 different ecosystems and over 2,000 plant and animal species. Visited by over 17 million people per year, the GOGA provides people a chance to experience their local biodiversity and local wildlife, to seek refuge from the consistently expanding urbanization in the Bay Area.
Invasive grasses like Festuca arundinacea, the tall fescue, Phalaris aquatica, harding grass, and the Earhartis species, the belt grasses, are currently threatening the safe haven of local biodiversity. Originally brought to California as food for cattle, these grasses have invaded local grasslands and coastal scrub habitats, including those in the GOGA, and outcompeted local plant life. But how did these invasive grasses enter parklands like the GOGA?
Some scientists theorize that roads and trails play a major factor in plant invasion, acting as pathways down which non-local plants can invade a habitat. As how and where GOGA's invasive grasses spread is still being studied, we decided to see if roads affected these plant species. We attempted to determine if invasive grasses congregate near GOGA's roads. From this, develop a predictive map of where these invasive grasses are most likely to spread. To perform this analysis, we obtained sighting records of 4 invasive grasses from CalFlora, a citizen science website, and modeled the points' overall distribution using kernel density analysis to see which area had the greatest abundance.
As grass sightings showed the highest density in the Marin Headlands, the Presidio, and Muir Woods, we chose to look at invasive grass populations in the southernmost Marin County GOGA parcels and the Presidio GOGA parcel. The Marin study area consisted of 20 parcels across 8,216 acres of land. The roadways in this area consisted mainly of trails, with 2 main highways running through it, Highway 101 and Shoreline Highway. The San Francisco study area consisted of 13 parcels across 1,502 acres of land. This portion of the study area is covered in trails with 3 main roads, Highway 101, Park Presidio, and Lincoln Boulevard.
With a study area chosen, grass points were then joined with a multi-ring buffer surrounding the GOGA's road and trail dataset. The multi-ring buffer was set at 15 meters, 30 meters, and 45 meters in each direction of the road. Points that fell within each buffer zone were then summed to get the total number of points per buffer zone. Even at 15-meter scale, CalFlora's data directly supported the research that invasive grasses congregate near roads. Invasive grass sightings were considerably higher the closer to roads, providing that roads have some level of influence on where invasive species will travel.
Based on this, and what we learned from researching, we developed a habitat suitability model to predict the grass's occurrence using the GOGA's river, vegetation, and road datasets. Studies have concluded that habitat type and proximity to water increase the presence of invasive species, thus we assumed these would be good variables to use for habitat determination within the GOGA. We perform Euclidean distance analysis on the river and road datasets, setting areas closest to these regions as highly suitable for invasive grasses. We then took the GOGA vegetation dataset and set the grass's preferred habitats, like coastal scrubs and grasslands, as the highest suitable environment.
After we had all our data, we reclassified all the datasets to a 1 to 5 scale, setting areas of high suitability in each layer as 5 and areas of low suitability as 1. With all the variables ranked, we overlaid the roads, vegetation, and river datasets using a weighted overlay. Our overlays showed that though no area was perfectly ideal for invasive grass species in question, a reasonable portion of the study area, all the region in red in our suitability map, was suitable for these invasive species based on our parameters.
Though only 7% of the study area exhibited relatively high suitability or showed up red on our map, about 60% of the points from the CalFlora observations fell within these red regions. This shows that this predictive map, based on our assumptions on invasive species preference for habitat, water, and roadways, is grounded in some validity. Overall, our study did have some potential issues. CalFlora sightings are commonly made by enthusiasts or volunteers, and as volunteers may not venture too far off paths to report sightings, the data may not depict the full picture for invasive diversity. Taking this into account, our study can tentatively say that invasive grasses may exhibit greater density near roadways in the GOGA. As our habitat suitability map paralleled the CalFlora observations, we also can tentatively conclude that a large portion of the GOGA is suitable for these invasives. Further studies should utilize a broader data set that employs a more confirmedly diverse and continuous survey method. Despite the pitfalls in our study, analyzing the factors that influence invasive species colonization in the GOGA is overall beneficial for informing conservation efforts and helps protect our local Bay Area ecosystem.